Hello and welcome to another Kickstart problem. This is the 2021 round A rabbit house problem. The problem is rather simple. So you got a grid of n by n elements, which has many cells, and each cell has a random value. The problem is basically the difference in value between each cell and its neighbors is smaller or equal than 1. So basically, what I mean by neighbors is, for example, for this middle cell here, the neighbors are the cell at the left, right, left, right, up, and down. So for each cell, there are 4 neighbors. You should always ensure that the difference in value between this middle cell and all its neighbors is smaller or equal than 1. What that basically means is that the range of values possible for this cell here is either 3, 2, or 1. So the problem is to determine the minimum total number of boxes to be added so that the rabbit's house is safe. What that basically translates to is that we should ensure that the difference in value between all cells in this grid is smaller or equal to 1. And we're only allowed to add an integer or to add a positive number to each cell. So what is the minimum number required to obtain this condition right here? For example, in this specific example right here, if all these cells, so for this specific example right here, if all cells are zeros and the middle cells is a 2, what we could do is that we could add 1 for each of these cells right here, up, left, right, and down. So what you get is 1, 1, 1, 1. So, and the difference in value between these cells and its neighbors right here is smaller or equal than 1. So we meet the requirements, and the minimum total number to be added is 1 plus 1. 4 times it's 4. Is 4. So for that, my advice for you is to first of all go and try to solve this problem on your own. It's a really fun problem to solve, and you will learn a lot by doing that. That being said, once you figure out what you should do, basically the idea behind the problem, it becomes very simple. So you may notice here that it took me less than 2 attempts to solve this problem successfully. The trick here is to the cell with the maximum value will always remain unchanged. So that cell, always look for the minimum number of cells to change. So yeah, you can change, you have to change the neighbors of the cell with the maximum value, but that cell with the maximum value, you should not alter its value. Instead, what you should do is try to find the cell with the maximum value, and scan its neighbors, and loop around so that you scan the neighbors of each cell. And well, that is basically the idea, but forcing that would be rather inefficient. So what you can do is create a histogram of all values and their corresponding cells. So what we do have is a histogram that has 2 keys, 2 and 0. So you got 2 keys, 2 and 0, and you got 1, 2 and 4 zeros. 1, 2 and 4 zeros. So forget these guys right here at the corners. So you got 4 zeros and 1, 2. Alright, so you look at the maximum value, which is the 2, You look for it for the value of the key to in the dictionary, and you basically find the cell, and you try to scan its neighbors, and if any of these neighbors is different, has a value difference bigger than one, then you try to correct that. um, if you updated um, any of these cells right here, you should go back to your histogram and try to update it with the corresponding changes, and then you draw down these two from the histogram, and then you go and look for the next maximum, which should, in theory, turn out to be maximum minus 1, so 2 minus 1, which is 1. So how to sort a histogram? So all along we've been talking about the dictionary keys and the dictionary values. We haven't talked yet about this helper list right here. What we could do is create a sorted list. As we fill out this our dictionary, we always try to append that item to our sorted list, and with the right implementation of the append and the search function of our search list, we can hopefully create an efficient sorted dictionary. So what we could do is try to implement a binary search in our helper list, which has another cache for our search is top of its login, which is really efficient from the brute force and login quite again. Also for inserts, basically. While there are test cases, while there are more cases, we try to reset our output value. We try to input the number of rows and number of columns right here. Yeah. Um, so this is created to populate our histogram with all the values present in our rows. So what we do when we reset our indexers right here, we try to explore all the rows in an ascending manner. So we go row wise, so 0 1 2 3 4, and then we go column wise. So when we reach the final cell in our row, we reset the row indexer to 0, and we increase the column indexer by 1, and we continue. So while there are more cells, if the value in our rows in this specific cell, for example this guy, if the value is in the histogram dictionary, so what we basically do is that we check it, that a value is in a dictionary, which is the histogram right here. If it is, then we append this position in our histogram. So with that we know that there is also a cell that has a value, and its position is basically this position right here, this tuple right here. Otherwise we create a new array, a new key, and a value which has one value, which is the tuple right here, this tuple right here, this position right here. And we continue and we go. So what we do next is try to loop around in our histogram. So while we have still some values and some keys in our histogram, what we do is we do this function, this histogram.pop. So what I haven't told you this far is that this is basically a custom-made type of dictionary. So it isn't just a dictionary. I implemented my own dictionary to try to fit in the requirements for this specific problem. So it is a sorted dictionary for rabbit. So I only made updates and necessary changes to the functions that I need crucially to solve this specific problem. So this is a really important step And advice to remember when solving these kinds of problems is that you only need to spend um, as much efforts as necessary. So don't try to complicate, to overcomplicate stuff. This is a fairly simple problem, and my own implementation, regretfully, is rather complicated. So don't complicate it even more with more functions than required. All right, so we create our sorted dictionary for rabbit. It inherits from the standard dictionary in Python. So we override the init, and we create our helper list, which is the sorted list we've talked about. So yeah, so basically these are all native functions of the dictionary. So what we overrided is the set item. So when we set the item in our dictionary, for example, right here, when we set a specific value, what we do is that we look if it is present in the dictionary, then we append the position. So it1 is the position and it0 is the key, meaning the value of the cell, and this is the position. So if the key is already in the dictionary, then we append the position. Otherwise, what we do is that we create a new key with that position. So this is somewhat a repetition of the already implemented. So we shouldn't have bothered to do this right here. But yeah, so what we do, and this is the crucial part of this function. So this is this additional part that's not present in the standard dictionary. So what we do is we have to update the helper list, the sorted list, just as well, because we created a new key right here. So if the key is already present, then for sure it is in our helper list, in our sorted list. If it is already in the dictionary, it is for sure in our sorted list. So we shouldn't bother to update our sorted list right here. But if it isn't, then we have to update our sorted list. And to update our sorted list, what we do is basically a binary search. So we know that the list is already sorted because basically it is in the name, it's a sorted list. We give as parameters the helper list and the new value of the cell, and we insert. So what this does is that it tries to find the index of the value that's closest to our new value right here, the index of the value that's closest to our new value here, and we insert it at that specific cell so that the helper list is always sorted. So let's take a look at this binary search function. So what we do is that we divide our list by these indexes right here. So first of all, we try to look at the entire list. First and last are looking at the entire list. So first is 0 and last is the index of the last character in our list. And found is false. So while first and last don't meet, there's still some elements that we haven't looked around. So what we do is that we try to find the midpoint, and if the element at the midpoint is exactly item, then we found it, and the position is midpoint, and we return it right here. Otherwise, what we do is that we see if the elements that we're looking for is on the left or on the right side. So if it's on the left side, basically what we do is we try to bring our last indexer back to the midpoint. Otherwise, we try to update our first midpoint. We try to increase it so that it's the new midpoint. So it's at the midpoint. So it's to be more efficient, then it's midpoint plus one and midpoint minus one. Otherwise, this won't work because you'll have to or also modify this smaller than it will have to be smaller, not smaller and or equal. So these are crucial right here, plus or minus one, and either if you found it or not, then you try to return the position with the closest index. So this position right here, so if we haven't found, then the position, we take the position of the first indexer, which should always be smaller than the value we're looking at for, so that when we insert our item, we'll insert it in a manner that our list will always be sorted. Alright, so this is our sorted dictionary for rabbit. Alright. So what we do is we try to pop an element from the dictionary. So pop isn't really a function for dictionaries because dictionaries don't have an order. But what we have here is a sorted dictionary. So what we can implement our own pop function. So what we do is that we try to look for in our sorted dictionary for the last value, meaning the maximum value present in our dictionary. Then we try to create a tuple, the maximum value as the first parameter, and all the positions that the dictionary has of that specific value. So we delete the elements from the sorted list and from the sorted dictionary so as to pop that item properly, and we return the copy we created, meaning this tuple, to the output of this function right here. So back to our code here. So we pop the maximum value along with the positions to our current variable here. We try to get the cell value, the maximum value, our value as put here, variable right here, and for each position we try to check the cells item 1 and item 0 and item 1. So item 0 and item 1 are the E index and the G index of these cells right here. So to recap, because I've gone a little faster so to recap right here, we try to pop. So what our current variable will look like is something like this. As an example for this graph right here, the current, meaning the cell with the maximum value and the positions will look something like this, 2, and the positions, because we only have one cell with the value 2, there will only be one tuple and its value will be 1 1. E equals 1 and J equals 1. So this is an example of a current of what this current variable would look like. This value will take the value 2, and this item will take all the positions of the value 2. So there will be only one position, one value this item will take in this example right here. So what we do is that we have to check the neighbors of every cell. For example, for this cell right here, this item right here, because item would be this cell right here. So we try to check its neighbors. So the top, the left, the right, and the bottom. So what we do is we try to get the value, which is exactly this value right here. Try to get it from the table, from the rows graph. So if P, we try to check that the cell isn't at the leftmost of the graph, so that we can look at its left. And if the difference between the cell at the left, which is what this function does, and the value of our cell is bigger than 1, then we append it to our FIFO stack, first in first out stack, that we already defined right here. And we basically do that for all directions, or 4 directions: top, bottom, right, and left. And when we do that, we always try to check that we aren't at a limit of the graph. Otherwise, we don't continue right here, because this is an AND, not an OR. So if, for example, here P is equals 0, then it won't bother looking right here, because if it does, then it will throw an error, and we definitely don't want that. So we add an AND right here, and when it's 0, it doesn't bother looking right here, which is good, and which is what we want. So when we check all the cells that are neighbors of our item right here, then this FIFO stack will basically be populated with all the variables. You guessed it, all the variables that have a value that's bigger in difference than 1 with our cell. For example, this guy, and this guy. Suppose there was 1 in this cell, 1 in this cell, 1 in this cell. So the check cell function will only populate FIFO with this cell right here. Alright, so what we do is that we pop an item from the FIFO stack. We try to get its position. So this is the position of the item, and this is the value. This is the position of the item. We try to get its old value, which is this. So this is E and this is G. E and G. When we apply that to rows, it gives us its older value. And what we do is we try to update it with the val -1, which is the value for the current cell -1, because we only want the minimum number to append to our graph to attain our conditions. So we definitely don't want val, and we definitely don't want val plus 1. We only want val minus 1, because this is the smallest value we can append so as to verify our conditions. And what we do, remember this output value right here, it was 0 at first, but when we corrected a cell, when we updated a cell, then we basically appended a number to that cell, and we need to add that to the number of cells that we have updated, not the number of cells, but the number uh, of integers, the integer we have, the number we have appended to all our cells, which will be the output right here. So we append that with the val minus 1 minus old value, basically the difference that we have updated. So that what that would be right here is 1. So we update this guy with 1, so it will be 1 minus 0 plus 1. Alright. I'm sorry, minus 1. So 2 minus 1 minus 0, which would be 1. And remember our histogram, we need to remove an element from 0, because we don't have a 0 anymore here. We'll have 1. We have updated with the value 1, so we no longer have a cell with 0 at this position right here. So we try to remove that position from the histogram, and basically what that will do is that if this we only had one cell right here with that value, and we remove that, then the key would also be removed from the histogram. So that's basically a functionality of this line right here. So what we do, we have removed the older key, but we also need to add the new key, which is basically 1 for this example right here. So what we do, if there was already a 1 in our histogram, then we append this new cell right here, the position of this new cell. Otherwise, we try to create that key with the position as a value. All right. So what this would do is that while there are more cells to update, it will try to pop them from this FIFO stack and apply this whole procedure to those cells, and it will loop around until there are no more cells in our FIFO stack. When that's done, we go back to this line right here. So what this line right here does is that it checks if there is another cell with the maximum value, basically 2. If suppose this cell was 2, then it will start by scanning this cell right here, and then it will move to this cell with the value 2 just as well. It will apply the same procedure, and when there are no more cells with the value 2, then we will go back to this outer loop right here. We'll check if histogram has more values that we haven't checked for, basically smaller values than 2, which will be 1, because we have updated our histogram with more value more keys of 1 that has. Alright, so it will pop that into this current variable right here, and it will set this procedure right along. So yeah, what that would do is that even if we have updated this cell with 1, it will have to check the neighbors of this cell just as well. So it will check this guy and this guy, and as these have only already a difference small equaling -1, it will not modify these cells. Alright, so that's basically what we have done in this script right here. And when you run this script, it passes all test sets successfully. So thank you, and I will try to post the code for this specific problem in the description of this video.